Okay, we're on lesson 6.1. Again, this is S6 4.1 because this is taken from a different textbook. The title of it is Antiderivatives, Indefinite Integrals, and Simple Differential Equations. We're actually focusing on antiderivatives and simple differential equations for today. So, as we say, integrals are just antiderivatives. They are derivatives but backwards. Early in the previous chapters, I believe in either three or four, we did a little bit of preview of, hey, what did you do to take the derivative to get this equation, and then we went backwards. And if you recall, we had this C going on here. We had this constant going on because when you take the derivative, any constant becomes zero. So when you go backwards, you got to keep in mind that, hey, you still have that constant. I don't know what it is, but there is a number there. So you want to make sure you take care of that possibility. Okay, so we have a couple of things that we know. For example, we know the power rule. So there is a power rule backwards, which we'll go over. We have some of the derivatives of our antiderivatives of our cosine, our trig functions, right? So if you remember that the derivative of sine is cosine. Therefore, if I had cosine here going backwards, my original function would be a sine function. If I have a positive sine function, well, cosine gives me a negative sine. So if I have a positive sine, I got to go backwards and get a negative cosine, right? The derivative tangent is secant squared, so naturally if I have secant squared, I go back to tangent. If I have cosecant squared, it goes back to negative cotangent, and secant tangent goes to secant, and cosecant cotangent goes to negative cosecant. Now you may be wondering, you see a single cosine, you see a single sine. What about a single secant, a single cosecant? What about a tangent and a cotangent? We'll definitely get those a little bit later, but right now these are the derivatives you had from first semester. Now going backwards to look at the derivatives and what you had now to go back and say, hey, what was it before to get this derivative, right? So that's why you have that derivative chart here to kind of remind you, hey, this is derivative, and these are the things backwards, okay? If you can, please make flashcards. I think flashcards are super useful in this case. But again, it's really up to you. I can't force you to do that. I think it's a good idea, okay? All right, so remember last semester we did guess and check, and that wasn't very helpful. So how do we do power rule officially, right? So here you have 9t squared minus 4t plus 3. Now, I know not a lot of people like this variable t, but t is very useful for us because it's time, right? So we're going to be comfortable using this variable. So your coefficient is 9. 9 still stays there. This is power rule backwards. When we're taking the antiderivative, we're going to take our power, we're going to add 1 to it, and divide by the new power, right? Remember, derivative was dropping the power down, so you're multiplying, and then subtract 1. So completely backwards says add 1, and then instead of multiplying, we're going to divide, okay? Same thing, you have your negative 4, you have t squared, and then divide by the new power. And if you have a single number here, no, there's not a constant anymore. This was the coefficient of your variable, so don't forget to put a 3t, put a t there. And lastly, there's always a constant after that. Okay, so you clean this up, you get 3t cubed minus 2t squared plus 3t plus c. The beautiful thing about antiderivative is that when you are at this point, you can always check. You can check by taking your derivative and say, hey, if I were to take the derivative, I get 9t squared minus 4t plus 3. Exactly what I get here. Right? And the c is a constant that goes away. So antiderivative is a really good way to check our answer, right? Because we can always take the derivative and see if we get the same thing back. And that way we know we're on the right track, okay? All right, so you don't have to do this. That's why I'm going to erase this because it's not officially part of my answer. What about something like this? Well, something like this, I would go ahead and change it into a power form first, because remember, any roots, any rational exponents, any fractions, if I rewrite them all as exponents, I can use the power rule on this. So if I were to go ahead and rewrite, I'm not taking the antiderivative yet. If I were to rewrite this is z to negative 3 minus 3z to negative 2 and dz, right? Notice when I took the antiderivative in the first problem, that dt went away. So essentially, you can look at it as when you're taking the antiderivative, this and this will cancel each other out when you're taking the act of taking the antiderivative, okay? So same thing, I'm going to do the antiderivative, so these two things will kind of cancel each other out. I now look at the power, z to the negative 3, so negative 3 plus 1, so that's negative 2, divided by the new power, minus 3, that's your coefficient, z, negative 2 plus 1 is negative 1 over the new power negative 1. Lastly, don't forget plus c. Always remember plus c. Okay, so I'm going to rewrite this because it's always better to write it back as a fraction. So -1 over 2z squared plus 3 over z plus c. And then that would be my final answer. Okay. All right, well, what about product rule? There's a product here. Well, I would suggest then, again, rewriting, multiply this whole thing out. If you were to FOIL or distribute or multiply this whole thing out, you would get 9x squared minus 6x plus 1. And now this is a polynomial function, and you can take the antiderivative like you would. So 9 is my coefficient, x cubed over 3 minus 6x squared over 2 plus x, because 1 times x is x. Don't forget your plus c. Clean up, 3x cubed minus 3x squared plus x plus c is your final answer. As you do more and more of this, if you're getting comfortable, you don't have to write out the 9 divided by 3. If you can jump ahead and see that, okay, I have a coefficient 9, I have x cubed divided by 3, automatically I can reduce that out to be a 3. You can go ahead and skip this middle step and go to the final answer and say 3x cubed minus 3x squared plus x plus c. Just like when you were taking derivatives before, you at first had to take the coefficient and multiply together. You got comfortable, and then you could just go ahead and multiply and go. So same idea, okay? What about something like this? Well, when you have something like this in number 4, you don't have quotient rule in antiderivatives. So what you would do is you would actually divide this out using either long division or synthetic division, really up to you. I'm going to remind you of what synthetic division is. All right, so synthetic division says this is really x cubed minus 1 divided by x minus 1. First thing you want to do is make this x minus 1 set it equals 0 and get x equals 1. Then you put 1 in this little corner here. And then you put this with your coefficients all lined up. So the coefficient of x cubed is 1. There's no x squared. There's no x. And there is a last coefficient of -1. Synthetic division says drop the first term. Then you multiply that by this 1 here. So you put that there. Add them up. You get 1. Multiply it again with the 1 here in the corner. Add them up. And then again multiply and add. You should get a 0 if it cleans up nicely. So your final answer would be 1x squared plus 1x plus 1. So x squared plus x plus 1. So this division problem can be rewritten now into the integral of just x squared plus x plus 1 dx, because that is the answer to dividing this problem out. Okay, now this is a polynomial function. I can go ahead and work this out. I take x to the third power, because it's 1 power more, divided by the new power, plus x squared divided by 2, plus 1 times x is x, plus c. Since there's nothing to reduce out, I am done with my final answer. Okay. All right, let's take a look at trig functions. So for trig functions, it's actually a little bit trickier because you want to see if you can clean it up first before you do anything with it. So first thing I recommend is anytime you have a coefficient like the 7 here, I would move the 7 outside. So you have a coefficient here, 1 over cosecant x dx. Then I ask myself, 1 over cosecant. Cosecant is already a reciprocal. Cosecant is 1 over sine. So 1 over sine is really sine x. Now that's doable, right? Now I can go ahead and work that out and look at my chart above and say, all right, well, the integral of sine x is negative cosine x. Don't forget your plus c because you took the antiderivative, right? You'll get negative 7 cosine x plus c to get your final answer. Okay. All right. Sorry, a second here. Thank you. Okay. Next, what about this problem here? You have 1 plus cotangent square z times cotangent z and then over cosecant z. So that's a little bit weird. So let's see if we can clean this up. If you remember back in trig, there is an identity, a Pythagorean identity, right? So the one I always memorize, because I don't take time to memorize all of them, the one I always memorize is sine squared theta plus cosine squared theta equals 1. All right, right now I'm dealing with cotangent. To get cotangent, that's cosine over sine, cotangent squared. So if I divide everybody by sine squared, divide everybody by sine squared, divide everybody by sine squared, I get 1 plus cotangent squared equals cosecant squared. Awesome. So now I can do this and replace it with cosecant squared. I can replace this whole thing with cosecant squared. Okay, Not taking an antiderivative yet. I'm just trying to simplify this, clean this up so I can actually do something with this equation, with this integral. So I'm going to replace the parentheses with cosecant squared z. You have cotangent z all over cosecant z. And then you can see this will reduce out because you have cosecant squared and a cosecant on the bottom. That will reduce out. So your problem now is simplified down to cosecant z, cotangent z dz. And then if you look at your chart above, this is already one of the answers. This is already one of the rules. The integral of cosecant z and cotangent z is negative cosecant z. And then don't forget your plus c. Your equation is now much easier. Okay. All right, next problem. I have secant w, sine w, cosine w. If you look at your chart, you'll notice that secant needs to be paired with tangent. We actually do have tangent. You take a look here, I have sine w over cosine w. That is tangent w. So I'm just going to go ahead and rewrite this into secant w, tangent w, dw. So then I look at my chart. The antiderivative of secant w, tangent w is just secant w plus c. Okay. What about a problem like this? The integral of the derivative of something. So think about it. The derivative of something, right? And then the integral is the antiderivative of it. So doesn't the integral kind of cancel out the derivative, right? The integral says, so again, if you were to look at this problem, you're going to look at it inside first. So the derivative of this is something, but then the antiderivative says, hey, go back again. So it gets rid of what you did, the operation you did. So it comes back to this original thing. However, because you're taking the integral of it, you must include a plus c because there's always a constant once you take the integral. So a problem like this is actually kind of funny because it's now just the same function inside, but plus c. Okay, so a quick way to remind yourself of what this is really doing is that when you have integral of d dx of a function, you get that function, but you get the plus c. If it's the other way around, you're taking the derivative of the integral of a function, then you just get your function, but no plus c because you're not taking the antiderivative. Only when you take the antiderivative will you have a plus c. Okay? All right. Now these are differential equations. Remember that plus c? That c is kind of annoying to me because I don't know much about it. So what I'm going to do is I'm going to give you more information so you can help me figure out what the final answer is. So the first piece says the derivative is already this. This is already the derivative. How do I get what it is before? I need to take the antiderivative, right? So if you start out with f prime of x equals 12x squared minus 6x plus 1, if you were to take the antiderivative, the integral of both of them, right? The first one will give you back to f of x because the antiderivative of f prime, which we just did in number 8, integral of f prime is going to be f of x, original function. This one's going to be 12x cubed over 3 minus 6x squared over 2 plus a single x plus c. Okay, I'm going to clean this up. F of x equals 4x cubed minus 3x squared plus x plus c. Okay, that's beautiful. Now, I'm giving you a second piece of information. F of 1 equals 5. So when you plug in 1, your f of x is 5. So your y equals 5 and your x is all 1, right? Based on that piece of information given to me there. 1, 1, 1. Okay, so now I just do the algebra and clean this up. 5 equals 4 minus 3 plus 1 plus c. That's 5 minus 3 is, 4 minus 3 is 1. 1 plus 1 is 2. 2 plus c. c equals 3. So what you always want to do is always want to go back and plug it back in, kind of like when you did algebra 1, you did y equals mx plus b, you solve for b, now what? Put it back in the equation and write it officially. So officially, my equation is f of x equals 4x cubed minus 3x squared plus x plus 3. And you can, again, check. You can check by plugging in 1 and see if you get 5. And then you can also take the derivative of this and see if you get 12x squared minus 6x plus 1, right? Again, lovely way to check, okay? All right, what if it's written this way? Well, it's the same idea. So we're gonna start off with our problem. dy, remember how separation of variable was a long time ago? So what you wanna do is you wanna move this dx over. So 4x to 1/2, and put your dx here, okay? And then when I take the antiderivative, when I take the integral, remember how I said it kind of cancels each other out? Well, when the left side cancels, the antiderivative canceling the dy out, it leaves me with the variable y, because that dy says my variable that we're deriving with is the variable y. And then the other side, the right-hand side of dx tells me we are dealing with a variable x. So you get 4. Okay, now we're dealing with fractions. We haven't done this before. X to the, so 1/2 plus 1 is 3/2. You're dividing by 3/2. Remember, when you're dividing by a fraction, you're really multiplying by a reciprocal. So you're multiplying by 2/3. And once again, there's still a plus c. Cleaning this up, I get 8/3 x to 3/2 plus c. Okay? Now, same as before, I gave you some information. I said, hey, y equals 21 if x equals 4. So 21, right? And then you have 8/3 x to 3/2 plus c. Now, instead of 4, because I see the 3/2, I think it may be easier if I plug in 2 squared. Because now I can use the square and reduce that out, leaving myself with 2 cubed, right? So you get 21 equals 8/3 times 8 plus c. 21 equals 64/3 plus c. I'm going to change the 21 to 63/3 equals 64/3 plus c. So c is negative 1/3. Okay. All right. So same thing before. We're going to put it back in so we can have a final answer, right? So y equals 8/3 x to 3/2 minus 1/3. Putting the c back in to this point right here. There's your final equation. Okay. So we have f prime. We went backwards one time to get our f function by our original function, right? What if you have f double prime? What if you have the second derivative? Well, then I will need 2 pieces of information, because then I can go one time backwards to get f prime and then go one more time backwards to get the original function. So I need information for y prime and I need information for the original function, so I can figure out the c's in 2 steps, because when you're doing twice, you have 2 c's. All right. Your book sometimes likes to call it c and d. I just call it c because it just keeps getting replaced, so it really doesn't matter what I call it. Okay, so I have dy squared equals 3 sine x minus 4 cosine x dx squared, right? Because we have separation variable, y on one side, x on the other side. Okay, I'm going to take the antiderivative. When you take the antiderivative, you only cancel out one of these dy's and dx's. So you have dy equals, okay, so this is a little bit trickier, 3 sine x. So 3 is there. The antiderivative of sine x is negative cosine x, so negative cosine x minus 4. The antiderivative of cosine x is positive sine x, and then you have your dx here. Okay, then you got to move it back. It's just a little bit of a process here, because now I can say y prime equals 2 if x equals 0, right? So y prime is dy over dx. So 2 equals negative 3 cosine of 0 minus 4 sine of 0. Okay, let's work that out. I get, oh, don't forget it's plus c. I forgot my plus c. Otherwise, I'm like, what am I solving for? Plus c. All right, 2 equals negative 3 times cosine of 0. Cosine of 0 is 1, so that's negative 3. Minus 4 times sine of 0, that's 0. Plus c, so c equals 5. So at this point, I'm going to put it back into this equation right here. So dy equals negative 3 cosine x minus 4 sine x plus 5. And I'm going to put the dx back here because we got to go one more time to figure out my original function. So take the antiderivative one more time, right? So I get y equals negative 3. Antiderivative cosine x is positive sine x minus 4. Positive sine x is negative cosine x, so it's negative cosine x plus 5x plus c. Okay. And now it says y equals 7 if x equals 0. Okay, so y equals 7 if x equals 0. So negative 3 sine of 0 plus 4 cosine of 0 plus 5 times 0 plus c. So plug in all the zeros in, 0, 0, 0. That would give me 7 equals that 0. 4 times cosine of 0 is 4. And then this is 0 plus c, so c equals 3. All right, I'm almost done. This is my final step now. My final answer is y equals negative 3 sine x plus 4 cosine x plus 5x plus 3 to be my final equation. Again, the beauty of this is you can always check. You can take one derivative, check and see if you got the same thing for your first derivative, then take the derivative again, get a second derivative. Also plug in your values and see if you got the right information that is given to you in the problem. Okay. All right. Lastly, same thing, it's just different notation, but it's the same information. So I have f double prime of x equals 4x minus 1. I'm going to take the antiderivative. That way it'll give me f prime of x equals, now again, you have 4x, so 4x squared divided by 2, that gives you 2x squared minus x, don't forget your plus c. So then I can use this first row of information. Negative 2, that's my y value, is equal to 2 times 2 squared minus 2 plus c. So 2 times 2 squared minus 2 plus c, I get negative 2. 2 times 2 squared, that's 8 minus 2 plus c. Negative 2 equals 6 plus c. C equals negative 8. All right, put it back into my equation right here, this equation. So f prime of x is equal to 2x squared minus 8, x minus 8, right? All right, one more step. I'm going to take antiderivative one more time, and I will get f of x equals 2x cubed over 3 minus x squared over 2 minus 8x plus c. All right, I call it c again because it doesn't matter. You can call it d. All right, the original information says f of 1 equals 3. So this part says f of 1 equals 3. So that means this is 3. And then my x values are 1. So plug in the 1, 1, 1, 1. I get 3 equals 2/3 minus 1/2 minus 8 plus c. All right, so this requires a little bit of finessing because you're trying to figure out all these fractions, right? So 3 equals, I'm going to make them all common denominator of 6 because I think that is the best common denominator. So if everybody's a denominator of 6, I get 18 over 6 equals 4 over 6 minus 3 over 6 minus 48 over 6 plus c. That's 18 over 6 equals 4 minus 3, that's 1, minus 48, negative 47 over 6 plus c. So if you add that over, you get 65 over 6 equals c. Okay. All right, so now don't forget to put it back into this f of x equation. So to finalize your answer, you will say that your final answer, f of x equals 2x cubed over 3 minus x squared over 2 minus 8x plus 65 over 6. So this is your final answer. So tonight's homework, you're just practicing a lot of these antiderivatives, try to figure out all the different tricks and rules, especially focus on the trig ones because the trig functions are a little tricky. Most of the time, if you clean up a little bit or do what you want to, do what you can in the beginning of the equation, then getting the antiderivative will be a lot easier. Yeah, most of the time that will be the case. Okay, all right, that's it, guys.